Hello, this is a key to the content checkpoint for the constant acceleration particle model. The first thing I'll have you do is look over this list of skills that you should know going into this exam. Pause the video, look them through. As always, whenever I give you one of these content checkpoints, these skills are really telling you what to study and what to make sure that you're good at, because we'll be using these very frequently throughout this entire process. So these are the very basic skills that you have to have. All right, moving to this first problem. This first problem has to do with a bunch of different word problems that we'll be doing that involve objects that are accelerating. And so, for instance, here I give you a situation. It says a car travels with a constant velocity of 15 meters per second for 25 seconds. It enters an on-ramp and accelerates from 15 meters per second to 31 meters per second over the course of 8 seconds. And I asked what distance it traveled and what its acceleration was while it was on the on-ramp. Well, for this one, the first essential skill you have to have is being able to turn this into a velocity versus time graph. Constant velocity on a velocity versus time graph looks like a horizontal line. So we've just got a horizontal line going across for a while. This is at 15 meters per second. And then it says that it accelerates upward. So we have here an acceleration upward to 31 meters per second over the course of 8 seconds. So this is accelerating upward at this point, and it happens over the course of 8 seconds. So we go up here to 31. All right. It was doing this first thing for 25 seconds, and then we have an additional 8 seconds here, so it goes up to 33. All right, and then it asks for the distance it covered. So to do the distance, we have to figure out the area underneath this curve. All right, so there are two shapes here, generally speaking. I'd say that there's a triangle and there's a rectangle. The rectangle has an area of 15 by 33. So we say 15 times 33. Plus the area of the triangle. The triangle has dimensions of 8 seconds along the bottom and 16 meters per second along the side. So it's 1/2 times 8 seconds, and that was because we were going from 25 to 33, times 16 because we were going from 15 meters per second up to 31. All right. And you add those together, and you should get 559 meters per second. I'm sorry, that's just meters, because it's a distance. Alrighty. Going on here, we're going to calculate the acceleration. The acceleration is the change in velocity over the change in time. It went up by 16. The velocity went up by 16 over the course of 8 seconds. So 16 over 8, that should give you 2 meters per second for the acceleration. Alrighty, moving on to problem number 2. We've got a ball, it's rolling up a hill, so someone's like stood at the bottom of the hill and they like chucked it up the hill, and so it's rolling up a hill, and it has an initial velocity of 16 meters per second. So going up the hill, the ball experiences an acceleration of -2 meters per second. The ball reaches the top of the hill 4 seconds later and continues along a level surface at a constant velocity for the next 6 seconds. And I asked how far the ball traveled over the course of its motion. So in this one, we start out at 16 meters per second, but then the ball is slowing down as it's going up the hill. So it slows down, then it gets to the top of the hill, and it rolls with a constant velocity after that point. That way, so we've got a horizontal line. So on this, again, we got to break it down into some different sections here. We just want to know how far it traveled. There's some things that are a little bit confusing, so I'm going to break it into these two shapes. We've got a triangle and we've got a rectangle here. The big confusing part here on this one is we have to figure out how much our velocity changed. Change in velocity is equal to acceleration times time. This is just a rearrangement of the slope equation for a velocity versus time graph. All right. So normally it's change in velocity over change in time equals acceleration. If we multiply both sides by time, we get this equation, change in velocity equals acceleration times time. All right, which in this case equals, and if we're talking about a side length here, this would be -2 times t, but in this case, we're talking 4 seconds. All right, and we're talking our t, so t is 4 and our acceleration is 2, so it ends up being 2 times 4, which equals 8. Some of you might have wanted to put in -2 there. That's fine. The thing is, I just want you to realize and recognize that it's a side length here. So I kind of leave it as positive when I'm calculating the area. So the side of this triangle here, from here to here, that's 8. All right, and it actually turns out that we've got 8 below as well. So it ends up, because it's 16 is the initial velocity and it goes down by 8, we end up with this being at 8 and this being at 16. And so it kind of cuts it right nice and evenly there. So in this one we have a rectangle. The rectangle goes the entire length. It was 4 seconds and then it traveled at constant velocity for another 6 seconds, so a total of 10. On this one then, the area of the rectangle, that equals 8 times 10, which is 80. Plus the area of the triangle, that's 1/2 times 4 times 8. All right, that equals 16. 80 plus 16 equals 96 meters. All right, and that is how that one works. Going on here to problem number 3. This is where they start getting a bit trickier. So in this one, we've got a penny. It's being dropped from the Willis Tower. It says, assuming that it starts from rest and it experiences a constant acceleration of -8 meters per second, how long does it take to reach the bottom of the tower, and how fast would it be going when it struck the road below? So on this one, what I'm going to say here, our velocity starts out at 0 because it says that it started from rest. All right, and then acceleration is negative, so velocity is going down this way. That's a straight slanted line. So on this one, things we know that the area of this whole thing equals 442 meters up in this area here. All right, so we have to figure out what the dimensions are here. We don't know a lot about this situation. I'm going to call this time here. This side here, time, we don't know what the time is. We also actually don't know what the change in velocity is either, but we know that the change in velocity equals the acceleration times time. And this is again where I'm going to do that weird thing where it's the side of a triangle, so I'm going to leave it as positive, but keep in my mind that it's actually going down here. And so we get 9.8 t. All right, and so I've got a triangle here that now has sides of t and 9.8 t, and it has an area of 442. So I know half base times height, 1/2 times t times 9.8 t equals 442. If you multiply this out, you end up with 4.9 t squared equals 442. All right, divide both sides by 4.9. Take the square root. You should get that t equals 9.5 seconds. So that asked, how long does it take to reach the bottom? So this is one of our answers. The next thing we need to know is how fast it's going to be going when it gets there. So to do that, we need to complete this delta V equation now that we know what time is. So this equals 9.8 times our time, which was 9.5. 9.8 times 9.5 equals 93.1. So this is our delta V again. All right, so our velocity changed by 93.1. Now, something to consider here, the velocity went down. If you look at the velocity versus time graph, the velocity is going from 0 into the negative direction. And so here, if we're looking for our final velocity, all right, and velocity is going down, and the change was 93.1, our actual final velocity is equal to negative 93.1 meters per second. All right, because, to symbolize that the velocity is in the downward direction. Problem number 4 here, pretty tricky on this one as well. It says here we've got an object that starts from 25 meters per second, experiences a constant negative acceleration over the course of 15 seconds. In that time, it travels a total of 250 meters, and I want the object's final velocity and acceleration. So in this one, it's kind of hard to tell. It's meant to be sort of implied that it doesn't hit 0 for its velocity because we know it's 15 seconds, right? And if you went all the way down to 0, for instance, here, and it was 15 seconds, we'd have a 25 by 15, all right, and 1/2 times 25 times 15. The area of this would be 187.5 if it went this way. And so that's kind of a clue to you that maybe that this isn't what happened, because if we have this as our area, 187.5, it hasn't even got to 250 meters, and then it starts traveling back in the negative direction, and so it never really reaches 250 meters if you go that way. However, if your acceleration is slower than that, all right, you accelerate something like this, all right, then we actually can reach 250 meters, but the math involved with this is a little bit more difficult. So the things that we know here, we know that we had an initial velocity of 25. That's here. We also know that the time in this situation is 15 seconds. So this side is 15. The tricky thing is this side of the triangle is delta V, and then you have to think, okay, what would be left then down there on the bottom? So whatever's left here is 25 minus delta V for the side of that rectangle there. And so we've got a triangle that's a 15 by delta V triangle, and we've got a rectangle that's a 15 by 25 minus delta V rectangle. And what we're going to do here is go ahead and calculate what that area would be. And we know it has to equal 250 meters because the area of this shape needs to be 250 meters because that's how far the object traveled. So we say for the triangle 1/2 times 15 because that's the base of the triangle times delta V because that's the height, plus 15 times 25 minus delta V because that's the sides on the rectangle. We know that this has to equal 250. We're going to do some simplification here. We get 7.5 delta V plus 375, right, minus 15 delta V. I'm just distributing here that 15 through, equals 250. All right, combine like terms, bring things to the same side. We get negative 7.5 delta V equals negative 125. All right, and then you solve that, and you get delta V equals 16.67. Now here's another one of these times where the delta V is actually a decrease in velocity. The velocity is going down over time. It starts at 25 and it goes down. It goes down by 16.67. And if it goes down by 16.67 and it started at 25, the place where it ends up, the final velocity, VF, that equals 8.33. And then the last thing it's asking here for is the acceleration. So acceleration here, we're looking at the slope here. The velocity goes down by 8.33. Oh no, sorry, the velocity went down by 16.67. And it did that over the course of 15 seconds. This should be negative because the velocity is going down. All right, slope is negative in this one. And you end up with negative 1.11 meter per second on that. Okay, number 5. Number 5 is another one of these that is going to actually end up with a quadratic equation in it. So what we have on this one, it says an object has an initial velocity of negative 12 meters per second. It accelerates negative 2.5 meters per second. And I said, given this information, how long would it take for the object to travel 117 meters, and how fast would it be going when it got there? So in this one, what we get, it's starting out at negative 12, and it's got a negative acceleration, so it looks like this. Negative 12 is where we've got there. We don't know how long it's moving. All right, so we call this side t, which means this side of the triangle is delta v. And delta v always equals a times t, which equals, in this case, negative 2.5 times t. And actually, I always keep these positive, remember, as I'm going through and doing the geometric analysis, because I consider this a side length. So I'm just going to call that 2.5t for now, because we're going to be calculating areas with side lengths and things like that, and it just makes more sense for it to be positive as we go through the work. All right, and so what we end up with here is we have the rectangle, which is a t by 12 rectangle, so 12 times t, plus the triangle, which is 1/2, times t, and then the height of that is 2.5t times 2.5t. And we know that this equals the distance traveled because the area equals the distance traveled. In this case, it's 117 meters. And so if you do some rearranging and simplifying of this, you should get it equal to 0. We should have 0 equals 1.25 t squared plus 12t minus 117. That's just a rearrangement of the same equation. All right, and then you can do the quadratic formula on that. That's the negative b plus or minus the square root of b squared minus 4ac over 2a. You get a couple of times in there. One of them is positive, one of them is negative. We're going to use the positive time, all right, because that's the one that makes sense. All right, so for this, you end up getting t equals 6. All right, and if t equals 6, we can figure out what the change in velocity is. Then change in velocity is going to equal 2.5 times 6. We do that, and we get 15 for the change in velocity. Now our velocity was negative 12, and the velocity is going down further. That delta v takes it down further, so it goes down 15. So going down 15 beyond negative 12, we end up with our final velocity equal to negative 27 meters per second. Okay, so that is those. The quadratic equation problem is a little bit long, and so if it's going to be on the test, it's going to be something probably like a challenge problem, but make sure that you understand the work there, and hopefully you come to the test with the quadratic equation in your back pocket, because it might be useful on some of these problems. Okay, so for the next section here, what we're doing is we're making qualitative representations of motion based on the representations that were given. And so first of all here, for problem number 1, what we've got an object. It starts off with a negative slope there, and then the slope is becoming less and less and less negative. It's flattening out. And so if we've got a negative slope and it's flattening out, it looks like this. All right. The acceleration, if you look at the slope of the velocity versus time graph, looking at the velocity versus time graph, the slope is a positive slope. so that means our acceleration is positive, so that looks like that. For the motion map, actually, motion map and written description, for both of these, you kind of have to realize what's going on here with this. This object is traveling in the negative direction. There are a few hints of this. One, it's going down on the position versus time graph. That indicates negative direction. On the velocity versus time graph, it's below the t-axis. That indicates negative direction. So it's going in the negative direction, and as it goes in the negative direction, it is slowing down. All right, so for our motion map, the way we show an object traveling in the negative direction and slowing down, traveling in the negative direction means that we have, it needs to be slowing down, so I'm going to make that arrow a little bit longer, that we're going off here to the left, and then the arrows are getting shorter if it's slowing down. So we're going to start here, long arrow, all right, and then we'll do a shorter arrow, and then even shorter arrow, and then really short arrow. All right, it looks like that. Okay, then we also need to have acceleration vectors on these. If it's slowing down, the acceleration vector goes the opposite of the direction of the velocity vector. So these are going here off to the right. The other reason we know that acceleration is off to the right is because if you look at the acceleration versus time graph, the acceleration is positive, so positive is off to the right. All right, and we put little tick marks on the acceleration to show that they're all equal. And so for the written description of motion, what I'm going to say here is the object has a positive initial position all right, and then it travels in the negative direction and slows down. All right, so that's what's going on there for that one. For this next one, again, we're given a position versus time graph. So if we're given the position versus time graph, we look at the slope to get the velocity versus time graph. It's horizontal there at the beginning of the position versus time graph. That means it has a slope of 0, which means our velocity is 0 for the first part. Then what happens is the velocity starts getting negative, and it gets increasingly more and more negative. All right? So that means our velocity starts getting negative, and it's getting increasingly more and more negative. It looks like that. For our acceleration, we're looking at the slopes of the velocity versus time graph. Slope of the velocity versus time graph at the beginning there is 0 because it's a horizontal line. Slope of the velocity versus time graph during the second part of the motion is negative. A motion map to show something that is standing still at first. Positive, it's going to start off here, positive, it's standing still. All right, and then it travels in the negative direction, and it's speeding up as it travels in the negative direction. So the arrows start off short, and then they get longer, and then longer. All right, and then actually, this one's kind of hard because it should end at 0. So what I'm going to do here to make this work right, this is kind of a trick. I'll draw my ending point first, and then I'm going to draw them back here, getting a little bit shorter each time. Well, I'm going to start that first one off really long. All right, and then we're going to get shorter, and then shorter, and then shorter. All right, and so it looks like this. So it just kind of worked backwards so that I got it so where it ended where I needed to. All right, so these arrows are getting longer. it's speeding up. That means acceleration and velocity are in the same direction. So all my little acceleration arrows need to be pointing the same direction as my little velocity arrows. And they're all the same acceleration, so I give them the tick marks like that. For the written description on this one, the object has a positive initial position. Object has okay, and then it's at rest for a time. And then moves in the positive direction. Oh, moves in the negative direction. While speeding up. Okay. So that's how that one goes. For this last one here, we've got an object. I've given you the velocity versus time graph first here. I'm going to assume that the initial position is 0. What we have is a constant negative velocity at first, and then it slows down. So constant negative velocity is a straight line this way, constant negative velocity for a little while. All right, and then after that it slows down, so it quickly slows down that way for our second period of motion. Then what we're going to look like here for the acceleration versus time graph, we use the slope of the velocity versus time graph. So for that first part, the acceleration is 0. Then you can see the slope of the velocity versus time graph turns positive at the end. So we've got a positive at the end. For the motion map, we've got an object, I said, assume it's 0 initial position, but it's going to be traveling in the negative direction, so that's kind of weird. So what I'm going to do, I'll make a spot over here. I'll call this 0. We'll start here. We're traveling at a constant velocity in the negative direction. All right, I'll just do that for a couple of seconds. All right, and then it's slowing down, so we're going to have some shorter arrows here. Just a little bit shorter, a little bit shorter, a little bit shorter. Okay. So that's what's happening there. During the first part, when it's at constant acceleration, we'll draw the acceleration vectors in there, but nothing is happening. Oh, I just realized here on this last one, I forgot the acceleration vectors up here. We need an acceleration vector for each of these moments where it's at rest. It should say that it's 0, all right, for the acceleration. So similarly here, while it's at constant velocity down here in this one, we've got 0 for the acceleration vectors. Then it starts to slow down. All right, so if it's slowing down, the acceleration is opposing the velocity. It looks like that. All right, negative. With negative velocity, positive acceleration on this one. For the written description, an object travels with a constant negative acceleration for some time. Okay, and then after that, it then continues to move in the negative direction. And slows down. Okay, that's how that one goes. Down here, we're doing quantitative kinematics graphs. So on this one, what we're doing is, it's basically similar to what we were doing on that last section, except there are numbers involved, so we got to be careful about that. So in this first one, we make a velocity versus time graph. It starts out here, slope is 0 for the position versus time graph, and then it's becoming more and more negative as time goes by. So we start out at 0, and we become more and more negative, like that. Okay, if that's the case, we have to figure out what this point is here. Things we know. We know that this happens at 3 seconds. All right, we know that the distance traveled over this is 9 because our original position was 9 and our final position is 0. If you look on that first graph, it goes from 9 down to 0 for our position. So we know that it's traveled a distance of 9 meters. That's the area here. All right, and so what we'll do is figure out what the side length is, because we know we can figure out what this change in velocity here is by saying we know 1/2 times length times height, or times base times height, is 1/2 times 3 times our change in velocity, whatever that is. We know that equals 9, the area of that, the change in position. And so what we end up with here is 1.5 delta V equals 9. Then we take 9 divided by 1.5, and we get change in velocity equals 6. All right, so then that allows us to figure out here that this point sorry, that's not straight. All right, that this point here is the point 3 seconds, comma, -6. All right, -6 meters per second. We know that this is negative because the velocity is going down as time goes by. The slope of the position versus time graph is becoming more negative. All right, and so then what we can do here is you can look at that and see that we've got a negative value for our acceleration because the slope of the velocity versus time graph is negative. To figure out what that acceleration is, we know that acceleration is equal to change in velocity over change in time. In this case, velocity goes down by 6. That happens over the period of 3 seconds. So we know that this acceleration here is at -2. And it's meters per second per second. Okay, that one's not so bad. We did a bunch of examples like that in class. This next one, we're going the other way. We're getting a velocity versus time graph. We have to make a position versus time graph from it. So in that first period of motion, what's happening here is it's speeding up and traveling in the positive direction because the velocity is increasing. So if we're speeding up and we're traveling in the positive direction, it looks something like this. Okay, it's curved. All right, and then we travel with a constant positive velocity after that. And actually, to try and make this look nice, I'm going to try and make that flatten out a little bit. Okay, and then we'll just keep going straight after that. So it's curved in the first part, but then it gets straight after that. And so what we've got here is a couple points. We've got the point here going up to the curved spot, and then we've got the second point where it's at the end of its constant velocity motion. To figure out how far it went in that first spot, we can find the area of this triangle. It's 1/2 times 2 times 5. All right, so the area of that triangle is 5. 1 half times 2 times 5 gives you 5. Then we can find the area of this rectangle. The area of this is 5 times 3, which is 15. All right, and so that allows us to get some points here. This one here happens at 2 seconds, and it's gone 5 meters in the 2 seconds. This one here happens at 5 seconds. All right, and it's gone an additional 15 meters. Oh, and so we're at 20 there. For our acceleration graph here, during the first period of motion there, it's positive. All right, and then after that, it's 0. All right, so what we can do then is try and figure out what the positive value is here. The slope in that first section, rise over run, it goes up 5, it goes over 2. So that means the slope here is 2.5 for the first section, and then it's 0 after that. All right, this last one here is a bit tricky, and I put it on here just to kind of give you one to keep you thinking. So what's happening here is we've got an object. It starts with a really positive slope, so a really positive velocity. It's kind of leveling off here, but it actually doesn't get to 0 in the end. You see this? It's still got a kind of positive slope here. And so I said on the velocity versus time graph, assume that the initial velocity is 4. So we're starting off here at 4, and we're going down. Now, if you had not realized and thought that this shape looked like this and went all the way down to the axis, you'd have that this side here was 4, all right, and then the bottom side was 5 because I had said 5 seconds, all right, and then you say this is 1/2 times 4 times 5, and you get 10 here for this area, and that looks like it went 10 meters, but it should have gone 15 meters in 5 seconds. So that's a clue that that graph is actually wrong. What this actually looks like, as I said, is it starts off with a really positive velocity, and the velocity is going down and getting less positive, but it doesn't get all the way to 0. So then this becomes one of those ones where we have to try and figure out what the velocity is, what the change in velocity is here. We know that it starts off here at 4. This is the general shape. All right. If that starts off at 4 up here, this side here is the change in velocity, and this side of this rectangle is 4 minus the change in velocity. So what we end up with is a triangle, which is 1/2. This whole thing happens over a period of 5 seconds, so we know this side is 5. All right, so 1/2 times 5 times our change in velocity. That's the area of the triangle, plus the area of our rectangle, which is 5 times 4 minus change in velocity. All right. We can simplify that, and it ends up giving us, you can bring things together, you get negative 2.5 change in velocity equals negative 5, and then you end up with the change in velocity here equals 2. All right, and so we end up knowing here on this one that our velocity it goes down by 2. Okay, and so that means that this one has the shape such that we get five, 5 seconds, 2 meters, because our velocity goes from 4 down to 2. It goes down by 2. All right, if we want to calculate the slope of this, it goes down 2. For the velocity versus time graph, it goes down 2 in 5 seconds. It's got a negative slope the whole time. Negative 2/5 is negative 0.4 meters per second per second. So that is how that one goes. Okay, so that is a lot, I know. I recommend that you really focus on trying to look at the different shapes of graph and understanding those. Also, look at the way that we use math in this. Identify when we use those changes in velocities, when we use some different formulas, when you have to put t in and solve for t. Try and figure out when those different situations apply. And I'm hoping after doing these practice problems and maybe looking back through your notes and the other worksheets that we've done, that you can get a pretty good handle on this and just make sure you take some time to prepare for this exam, because there's quite a lot on this and it's pretty confusing.